I am François Schmidt, research director at CNRS, working in Vimereux. And this is a short introduction to turbulence with ocean sciences in mind. So in the common language, we know turbulence because it was used for a long time for turbulent kids or turbulent crowd. But in fact, for now more than 100 years, it belongs to the field of physics, and more precisely to fluid mechanics. And you know already also this if you have taken the plane and if you have the bad luck of being shaked, like we can see here. So in fact, turbulence can be quite wild. Also, if you can also see the problem of this flight that has a problem to land. So in fact, it illustrates the fact that turbulence can be also large scale, and also it can be very it can generate huge fluctuations. So the plane here cannot land and it needs to go. So the general properties of turbulence is that it produces huge fluctuations, also stochastic properties, unpredictability, chaos, mixing. It's universal in nature. You can see turbulence in fluid, also in gas. You can see it in clouds, in stars. So the sun is a turbulent star. You can see it in rivers and also in the ocean. Also for engineering application, it's important. So we can see it for planes, for renewable energy, chemical reactions, and transport of particles. So this movie here illustrates the fact that, in fact, if you inject energy in the system and you stop it, then turbulence is also stopping. So turbulence needs to have energy injection. And we can see also that this energy goes from large scale to small scales. And at small scales, the energy is dissipated into heat. Another mechanism of turbulence generation is thermal convection. It's something you can generate when you cook and when you eat from below some water. So turbulence, you are generated at a certain level instabilities, and then it goes to turbulence. So it's here generated by a temperature difference. So the equations of turbulence are Navier-Stokes equations. So it belongs to classical physics. It's a subdomain of fluid mechanics. The equations are known for about 200 years now. So Navier proposed the equation in 1822, and a bit later Stokes completed the equations. So that's why we give the two names to the equation. And it's, as I said, universal in natural sciences, and all fluid, liquid, or gas follow these equations. The notion of scale is important in turbulence. Usually we consider elements of fluids which are very small, and then the fluid mechanics is built for these elements of fluids. Then we have at small scale we have viscous fluids, and above Kolmogorov scale we're going to see later what is this Kolmogorov scale. It is of the order of 1 millimeter. Then you have turbulent flows. So turbulence is usually considered to belong to scales between 1 millimeter and several thousands of kilometers. So what are these Navier-Stokes equations? It's simply, in fact, the fundamental equation of dynamics, which is called Newton's law, which is applied to the element of fluid. So if F, the force, equal m times the acceleration. And then we make use of a partial differential equation, and we obtain the expression which is here in the bottom, where we have on the left the acceleration, and on the right two types of forces. One is pressure force, and the other one is a viscous force. So Navier-Stokes equations are quite complicated, and it belongs to what is called the Millennium Problem. It was proposed by the Clay Mathematical Institute in more than 20 years ago. So they have proposed 7 mathematical unsolved problems, and they have given $1 million prize if you solve this one of these problems. So up to now, only one has been solved. So it's called the Poincaré conjecture, solved by Gregory Perelman in 2010. And Navier-Stokes, we can see here, if you click in this link, you will see the description of the problem and the fact that Navier-Stokes equation and the problem is still unsolved. About chaos, so Navier-Stokes equations are deterministic, so it means there is no randomness in the equations. And when we know the past and the present, then there is only one future. But they're chaotic, and there is sensitive dependence to initial conditions. And this is what is the general properties of chaos, which means divergence of trajectories. And because of chaos, there is randomness in the system, so measurements are very often irregular. We can see here this figure represents a high-frequency measurement of turbulence in the atmosphere. We can see that it's not smooth. There is huge fluctuations, and we need to understand this randomness. We need to use the probability theories and also statistical methods. And it's also a prototype of complex systems. So we have nonlinear equation with coupling. We have large spatial scale range between millimeters and kilometers. Also large temporal scale range between milliseconds and years, and very large number of degrees of freedom. So in general, in the field of universe sciences, which called in French sciences de l'univers, or geosciences, we have 3 categories of studies. One which are complementary. One is observation in the field. One is experimentation when you have controlled condition in the laboratory. And the last one is modelization, which can be stochastic or numerical. So I will have a short, also other short presentation in these 3 topics. And I finish with my books here. So thank you for your time.